you're ready.
Okay, fine. So the next speaker is Vincent Laurain. He will talk about water distribution network leaks estimation in faulty sensor context. Wow. Vincent is associate professor at the Université de Lorraine, is in the east of France. And Vincent used to be one of the chairs of the French National System Identification Group that is hosting you today. So Vincent, the floor is yours.
Thank you very much, Rashid. Good afternoon, everyone. So the work that I'm going to present to you today is a joint work with my ex-colleague, Samir, and myself. And the main topic is water distribution networks and how to estimate leaks in such a context. So just before I start deep into the subject, let me recall you some of the context. And the context is the following. So we are talking about water distribution networks. So really the networks that bring your drinking water at home. And little known fact, but actually currently in France, even in the best city, in the most modern cities, you can count with at least 20% of drinking water which is lost in the pipes due to leaks, mostly. So I let you imagine losing that much water. I mean, change context where water resources might be disappearing. And so if you are in the water management process, then what you want to do is detect the leak as soon as possible. But the problem is that often you don't have enough manpower or even enough money to cope with all the leak at the same time. So you need to detect them, but you also need to prioritize your interventions. And let's say, basically, if you have a whole network, then the problem might soon become the fact that for detecting leaks, you have to go on the field. You really have to search for them. And the idea, of course, since we have many data now, is whether we're able to identify the leaks and help the water management people to find the leak and to prioritize their interventions. Therefore, the idea of the project, which was, can we use the flow meters to detect leaks? So basically here you have a picture of the final result of the Sphero project, because this project has now ended. And what you see here is a real network in France. It's rural, so it's in the countryside. Every little scheme here is a little town, and every point here is a flow meter sensor. So we had like more than 80 flow meters. And at each point, we know in which direction the water flows. It's not always the case. So sometimes the water changing path. This is also possible. And we had 4 years of data, 4 years of flows recorded every 15 minutes. So this is the network I worked on. But for this talk, I'm going to focus on a very little part of the network, because everything that I will be said here is generically true, but it's much more easy to explain it on a small part. So here, these 4 sensors, these 2 cities here that I here present at this little scheme here. So we have 4 flow meters, and in between the flow meters, you have what we call district method area, DMAs, which are basically houses, villages, or pipes which consume water. And we have 4 flow meters recording every 15 minutes of flow. When I deal with data, I like to look at what the data look like. So let's first just look at Y3 here. 1 simple flow meters with water consumption of 1 village. And this looks slightly like that. So you have 4 years of data. The data looks messy is just because we have high variability between the night consumption and day consumption. So there is much more consumption during the day when you take your showers, when you take your bath, you might be, I don't know, going to the toilet, things like this. So everybody does that at the same time. We track the consumption. And normally at night, most of the people sleep. So the consumption goes down. Here you have -1s. The -1s indicate that we don't have data. So you have holes in the data. So data here is not present on the sensor, but sometimes the sensor really indicates 0 consumption, which is not true either. And what is really interesting is that even at the lowest points, you see that the real consumption never really reaches zero, because there is either night consumption, so people consuming water at night, or probably also leaks in your system. But I wanted to focus on this because when I'm talking about estimating leaks, you actually never really can estimate the true leaks on the system. You have to have a reference. So basically, if you think that your lowest point of consumption is a regular consumption, then what I will call leaks in this talk is anything which is the difference between this reference and the real consumption. Yeah. So there is no way of detecting true leaks. You can detect leaks up to a certain reference. What the water management people do is that usually they look at the night flow, because the night flow is normally known to be very little variating. Yeah, because if you have that many people in a village, then there is no reason why the consumption should change from one day to the other. And here, for example, if you have like that many years of data, then you can consider that at the minimum point of consumption here, the red line, the red dotted line, would be your reference. And so you can estimate leaks, which are the difference between the night flow consumption and this reference. What if the leaks appear during the day? Then that's another question. And of course, here, when I'm talking about reference, you can take any reference. So you can take a manually set reference, but you could also, and this is what we did a few years ago, make a real model of your consumption of this in the data on a couple of. Here you see the daily viability. So here everybody sleeps, and then everybody wakes up just before going to work. All the showers up in here. Then people go to work, and then at night when they come back home, there is a slight peak also. And it goes on like this. Probably during the weekend, the consumption is slightly different than during the weeks. But anyway, we can build models, and you see that if there is no leaks, then the model copes quite well with the daily viability. And if leaks appear, then the total consumption rises. But in any case, even if there was a leak appearing during the day, then you would be able to see the difference between the consumption and what your model produce. So here, just as a matter of vocabulary, I will call residual the difference between the true measurements in blue and the reference model, which in this talk, we use this kernel predicting model that we developed quite some years ago. So like what you can remember in a wrapped version is that if you have only data and you want to work from the data only, then your data series must contain at least a part where there was no leaks. But if you don't want to do it only from data, then you can ask the people which are well acquainted to the network, and they will tell you what is basically the reference, which could be set manually. So this is the context, yeah? And if we look at the small part of the network that I showed you, then if you're a water manager and you want to estimate what is the consumption here in the DMA1, so district method area 1, then what you will simply do is a water balance. You take everything that flows in through Y1, and you subtract everything that flows out through Y2 here and Y4. So the total consumption is just a simple water balance difference of Y1, Y2, and Y4. And here, the leaks, therefore, is the total consumption minus some kind of reference, this reference being set manually or by some kind of model. And here I raise to your attention the fact that you can either compute the reference directly on the DMA, but here in this example, the water is always flowing in the same direction. So basically you can also use the reference directly on Y1, the reference directly on Y2 and on Y4. And here we would call epsilon this reference signal. Whether you work in this configuration or this configuration does not have any difference in this talk. So you do that for all your DMAs. You have the consumption in DMA1, which is Y1 minus Y2 minus Y4 here. In DMA2, which is what is flowing in Y2 minus what's flowing in Y3. And there in Y3 and Y4, the consumption is equivalent to directly Y3 and Y4. So you have a simple and neat system to solve, and then you can estimate the leaks everywhere. And now this is where the problem starts shooting. Let's do that for the DMA1, the first one. And here, so if you do all that really neatly, this is what appears. So the first thing you can see is that you have missing data there. So how can you handle missing data? This is a question. But moreover, what you can see is that if you do that, you see that the regular consumption or the leaks that you estimate sometimes become negative. And this is highly abnormal. It means that either somebody's putting water in your network, but that never happens. So the cause must be really different. Yeah. So why is this consumption becoming negative? So let's have a look in details at the sensors. In blue, you have what's flowing in Y1. And in red, you have what's flowing in Y2. And here what you see is that there is a strong correlation between Y1 and Y2. And if you think about it, that's really kind of normal. Why? Because everything that flows through Y2 before that flew also through Y1. So this correlation is normal because normally the blue signal contains the red signal plus something else, yeah? So here, this is something to be expected. But if you look at Y4, then you see that between the blue signal, Y1, and the yellow signal, Y4, then you don't find this correlation. Y4 is sometimes jumping really high, and this consumption, this extra consumption, is not really present in Y1. And what is even weirder is that sometimes what flows through Y4 becomes greater than Y1. So it would mean that you would have more water here than here, and that's not possible. So the only conclusion of that, and this is really a realistic case, is that the sensors are mostly faulty. And you would be surprised how much faulty they can be and how often that happens. And therefore, the main problematic of this talk is that, is it possible to estimate the leaks in a sensor faulty context? The outline is therefore the following. I will present you how we model noise on the sensors. I will present some graph approach, and I will justify why we think it's really interesting to go through graphs. And then afterwards, I will really solve or present how we solve the problem of identification of leaks. And I will even present some results on the real data set at hand. So how do we model the noise? We took the most simplistic way, is that what you measure is actually a true consumption plus some default. So it's just a simple additive default. And therefore, the residual is the real consumption plus the default on the sensor minus the reference signal we talked about before. And here, keep in mind that potentially each DMA has leaks and each sensor might be faulty, and you don't know that. And if you integrate now the default in the system we had before, then on the left side here, you have all the defaults and leaks that might be present on the system. And here you have the reference signals, which are your measurements minus the reference, which can be a model or manually set. And the question is, can you identify the leaks and can you identify the defaults? If I mumble jumble around here, I can give a matrix equation of this problem, and you see what's appearing here. A matrix A composed of 1 minus 1. Here listed all your defaults at hand, possibly, and B, which is basically the matrix which is linked to the residual signal. And the problem is to estimate X, sorry. So here I know which community I'm talking to. And of course, everybody has seen there are 4 equations, there are 8 defaults. The problem is unsolvable directly, yeah? So that's clear because the number of unknowns is much greater than the number of equations. So it's an underdetermined problem. And of course, I can also spoil a little bit the end of the presentation, but we will use a regularized identification scheme. But how can we do it? And just before I answer this question, there is also a side question that appears. Let's say, even if you knew that not all these defaults are present, let's say you know there are a leak here and a leak like in DMA3 and in DMA4, and you know that your sensor 3 is faulty, and all the rest, you know there is no leaks and no default. Is it still possible to estimate these leaks and defaults? So there is an they're unknown. So you see that if you do so, you just need to take a few columns of your original A matrix, and then you have a new matrix problem, estimation problem, which is a sub problem of your original problem. AX is BY. And the question is, can we solve it? Is it possible to estimate L3, L4, and D3? And of course, again, I know the community and I know you all have the answer. The answer is very simple. Yes, we can, only if and only if the rank of A is full, or at least the rank of A is 3. And then you have the solution. So you go to your favorite water management guy and you tell him, yeah, it's easy. You can just check on the rank of A. But the guy, the answer is very straightforward. It tells you, but I'm not a mathematician. So how do I do that? And basically, what does it bring me? Because these matrices, I don't see the link between my original problem and these matrices. So the question that really arises here and is a lot more practical, I give it to you, but can we give a comprehensive topological answer to this identifiability problem? Because if you can do that, then you can really help them understand that problem. And there come in hand the use of graphs. So let's make a parallelism between the problem at hand and the graphs. If you look at the matrix A I spoke about before, you see it's only containing 1, -1, and zeros. And if you know a little bit about graphs, it will straight away strike you that these matrices, they look a lot like what are called the incidence matrices of a graph. So if you have a graph with vertices and edges, then the incidence matrix is defined by a 1 if an edge. So if you have an edge J that has an arrow leaving node I, then the incidence matrix of this graph put a 1 at the place Ij, and a -1 if the edge is entering the node, sorry. And you put a 0 if the edge is not incident on the node. So the intriguing question here is that, is there a corresponding graph to this matrix A? And actually it would seem kind of logical, because if you remember, these matrices, they actually are issued from water balance that kind of embed the topology, yeah? And actually the answer is yes. And what do these graphs look like? So first, let's look at matrix B. B is the one which is linked to the residual, to your measurement. And very simply, it's interesting that if you take the metric, the original matrix B, then the corresponding graph for this small part is this one. And here you clearly see that actually the topology of the graph at hand is exactly the same topology than the actual water network you have. And if you look at the incidence matrix of this graph, it's exactly B. At one little different detail is this node 0, which is not present here, which you have to add because otherwise this first edge here, yeah, would not be linked to any node, and this is not really good in graphs. But actually, it adds only a simple equation, the first equation in red there, and this equation is a simple linear combination. It's the sum of all the underlying equation of B. So the rank between B and I is the same. This graph I call the residual graph because it's the graph of residual. So if you have any network, it's very simple. You can build this residual graph by simply taking DMAs as nodes, and any sensor here would be an edge. It must be noted here, I make a small parenthesis. Usually people working with graphs and water network, they usually use the measurement as vertices and the DMA as edges. And here we have a dual representation. So in our problem, the graph that appears is the dual version of the usual graph used, where the measurements are the edges and the DMA are the vertices. Yeah. And what about the A matrix now? It's also very simple. So you have your residual graph. The corresponding graph to the A matrix of our problem now is the following one here on the right side. So it's very simple. If you consider there is a default on a sensor, then you make simply an arrow which goes in the reverse direction to the sensor. So if you consider that the sensor 1 is faulty, then make an arrow directed invertly of the measurement 1. And if you have a leak on a DMA, simply add an edge from this corresponding DMA to the 0 node created before. And if you do that, then the incidence matrix of this graph is exactly the A matrix at the sign, like there's difference in the sign, but it doesn't matter, of our original problem. So what does that mean? oh, sorry, I just forgot. Of course, you can make a fold graph also if you have a reduced number. So if you know only D3, L3, and L4 are present, then you can very easily build the corresponding graph for the same resulting matrix. So if I recall here, so we had, it's a small minor contribution, it's a practical contribution, but it's possible for the problem at hand to derive an algorithmic construction of the graphs. And what do you gain by graph? You have to solve AX is BY, but if you know that it's equivalent to solving the incidence matrix of the graph time X equals another incidence matrix of a graph time Y, and you know the rank of these matrices are the same, and you know that you want a full rank on A, then it means you need to have the same rank on this incidence matrix of the graph. So therefore, the question that arises is, can we characterize a full rank of A just based on topological condition on the corresponding graph? And here was the theoretical result of this work, is that yes, you can. And you can consider that the defaults are identifiable if and only if this graph is a directed tree. A directed tree is, to make it short, a graph where you don't have loops inside. And then that's nice, because if you go to your water management guy and you say, okay, let's say you have this water network at hand, and you would like to know whether a combination of a leak on DMA3, a leak on DMA5, a default and sensor 3, a default and sensor 4, and a default and sensor 5, is it an identifiable structure? So you could tell the matrix rank, which is one thing, but you can also say, just look at the default graph. And here I can straightforwardly tell you that this structure is not identifiable. Why? Because here you can clearly see this loop appearing in the graph, and you know this graph will never be identifiable. So you cannot detect a combination of leak 3.5 and default 3.5. It is not possible. And that is really nice in my sense for the water management guys, because they're able just at a glance to say how resilient is the network, the current network. Because you could say, if I didn't have D3, I know that the appearance of D3 or of a leak on 2 will make the problem unidentifiable. So it's better for me to prioritize an intervention. I should quickly solve the problem of default on sensor 5 or the problem of leak on 3, because if any other problem arises, then I will not be able to know really what's happening on my network. And another nice thing is that it's easy to do it with the eyes, but it's also easier to do it computationally. So if you want to compute the rank of a matrix A, then Gaussian elimination gives you a complexity in n cube. And I let you remember the number of sensors that we're dealing with here, so 80 sensors. But if you want to check if a graph is a directed tree, then it's only a complexity in n. And that also is very promising for extending this to many more sensors, yeah? So let's back to our original problem. Can we identify the leaks? Then what to do now when you don't know whether a given default is present? So you don't know if there is a default on the sensor. You don't know if there is a problem on the leak. The problem is underdetermined, and as I told you before, that will need some regularization. So, but you can also help yourself with other things, like, for example, physical assumptions. And you know that a leak must be positive. So you're not searching for all the structures, you're searching for the solutions where leaks must be positive. And if I put that mathematically, we propose the scheme where you have the original problem at hand to solve, AX is BY, but you can add a regularization term which will help you choose a preferable solution among the solution. And I will come back just in a second on what could be this regularization. And this problem is subject to the physical fact that leaks must be positive. Yeah. So how to choose R? There we didn't search really far. You can say, for example, what I consider to be the most probable solution is the one which explains the data with the least number of defaults. And therefore, if I have a solution with 5 leaks and a solution with 3 leaks, then I think the 3 leaks is basically fair. And this is a fair assumption if basically the water management deals with the leak quite regularly. Yeah. So you want to know the number of defaults present. You know that this can be characterized by a zero norm. The usual thing, we relax it as a L1 such that it becomes a lasso problem. So it's kind of a generic solution. You could think of other regularization. You can use the solution which is closest to yesterday. So if yesterday there was 2 leaks, then today we can cope with probably 1 default more or 1 default less, but it's really highly improbable that 3 defaults appear at the same time on the same day. Yeah. So in any case, it gives you another lasso. But you have a problem there, and this is what we experience, is that if you do like this with the lasso, you always end up with problems which possibly have multiple solutions, but the lasso is only able to give you 1 solution. And this solution will be highly dependent on where you start your optimization process. But if there are multiple solutions, it's really hard to decide algorithmically which is actually the most probable solution. It requires some kind of eye of an expert. So what we did is say, instead of giving 1 solution, which might not be the best, could we give all possible solutions? And of course, now we can. Why can we? Because thanks to our graph analysis, it is possible to determine for a given number of sensors and a given topology, all the possible identifiable default structure. And of course, you have to make the assumption that what you're studying, your leaks and default that you're studying, must be identifiable, because if they're not identifiable, in any case, you will never be able to give a proper result. So what we did, the strategy is just replace 1 quadratic optimization scheme, the lasso one, by multiple quadratic analytic solution. So we determine first all the identifiable structure for the problem at hand. And there comes in hand the fact that if you use the graph structure, then your complexity, your numerical complexity is n and not n cubed, just like for the rank of a matrix. And then for all the identifiable structure, you throw a simple least square, so the generic favorite method that you want. And among all the solutions, you only retain the one which have a physical plausible solution, meaning the leaks are positive here. And in the end, you will retain the 1 or more solutions which fulfill the regularization scheme that you would like. Yeah. So you can do it step by step. And doing so, then it's possible to display a range of solutions. Yeah. And it's also possible doing this structure if you knew that 1 sensor is always faulty and you know it from experience, then you, instead of here retaining only the physical plausible solution, then you can retain solution where D3 is present. So when you know that there is a fault on a sensor, you can also force the algorithm to give you only a solution that contain a default 3. And this is kind of nice, I think. Yeah. And we also raised the question beforehand, what if a sensor is completely down? Then in terms of graph, if your sensor 2 is down here, it means you don't have any data accessible on Y2, then simply merge the DMA2 and the DMA1. So you go to this structure. So it's also possible to summarize this in graph. And now if you estimate a leak on the new merged DMA1, 2, then what you can say afterwards is that this leak is either present the data that we had at hand, just using all of these concepts at once. This is the generic data, but don't worry, I'm going to zoom in. So just as a recall, I tried to mimic the structure. So you have the Y1 sensor, which is upstream, which splits between Y2 and Y4. And Y2 goes then to Y3 down there. In all the figures I'm going to show, and I'm going to zoom in, blue here is what the sensor measures. Green is these residual signals that I made. You remember, this is just the difference between the measurements. You have these green curves here everywhere. This is the residuals that I was talking about. Then what you have is the black line here is the leaks estimated on the DMA corresponding to the sensor. And if you have a blue region like this, it means that the algorithm throws not one solution, but many solutions, at least two. And we take the max and the mean to say, for example, at this point in time, here we estimate a leak that might be 0, but it might be that much. It might be 3 cubic meter. And I'm going to explain how it works. And we have the same on the defaults, but these curves are in red. So red is the estimated default curve. And if there are more than one solution, then we give a range of solutions. So let's zoom in to see what's happening here. First, on the left part of the region, one and this one. And here the estimate residual is in green, but you see that the actual leak that we estimate is mostly set on this downstream DMA, which remain the fact that actually there is a possible leak here on DMA 1. But since we merge DMA 1, 2, and 3, we don't know really where this leak can be. So we indicate it by saying, okay, look here. It's possible that at this point there is a 6 cubic meter leak, but this 6 cubic meter leak can also be there or here. Yeah, so this is the effect of merging. We have also regions where the results are not that good. And here, probably it will take you a lot of time to understand this. But if you really look in detail in consumption on sensor 1, and here we see there is a high jump on sensor 4. Somewhere here, this sensor is missing. And actually here we know for sure after talking to the one-term management people that this solution is not the good one. But we know why. It's simply because the real solution was one that did not fit our regularization scheme, meaning that here it's highly probable that there is no default on this sensor 1, but most probable here there is also a leak here, which is set on the default. But if you sum all the defaults, actually the solution that we give is minimal in terms of the regularization problem at hand, but the true solution does not fit our regularization scheme. It is still nice here, at least to see that on this region, this sensor is the faulty one. It was probably not well calibrated. So if there is a leak appearing, then the sensor is completely jumping. So you see that the residual here is high, but the leak estimated, and we cannot really say whether it's a leak or a default on the sensor. So the leak can be most probably here, which would kind of correspond to this jump that we have here. So it might not give the proper result everywhere, but when the conditions are met, we have the possibility to inform the water management guys that actually the leak is also possibly that low. It must not be that this leak is that much. It's also possibly a default range, yeah? And we have, of course, other possible solutions where it works really well. So here, from the upstream sensor, you see there is a leak appearing because the consumption is slowly rising, and then something happened and there is a jump. And actually what you see is that on the one hand, there is this slowly appearing leak, but if you just look at the residuals, you might panic because you see, wow, the leak is incredibly huge. But the algorithm is able to detect that the leak is much lower actually, and most probably it's an error of the sensor. So this is basically the error of the sensor that tricks you in believing that this leak is that much, when in fact the leak is detected by the black curve. And it's also correct to split the leak. There is a splitting leak, but we know it's not on this DMA because here the leak indicates 0. Then we go downstream. The leak is also present here, but the algorithm indicates that there is no leak there, and it correctly positioned the leak actually on the last DMA here. And everything that I'm telling you about is not only my interpretations of things, it's of course when we talked to the water management people that we had at hand. And this end my talk by saying that I presented you an approach, a complete approach to detect leak in water dynamical networks. And we took the realistic assumption, which we think is new in the literature, faulty. Here we call that the fault modeling that we put at hand is very trivial. It's just an additive default. But we could think about more in-depth method where you can also model the default, because a leak appears similarly like a leak as a really well-known shape. Either the pipe breaks and it's a high jump, or it appears slowly, and therefore we could make more improvement on that. And the contribution here is mostly the graph transposition. So the fact that we interpret the whole identifiability problem in terms of graph, which gives a neat understanding of the problem. We gave also sufficient and necessary identifiability conditions, and they are fully expressed in graph topology. And we propose a regularized identification scheme that we tested on real data. So let me thank you for your attention. And if you have any question, I would be really pleased to answer it. Thanks.
Thank you very much, Vincent. Wonderful presentation. I really enjoyed. We still have about 5–10 minutes for questions. So does anybody have a question?
Yes, Martin.
Yeah, please.
Thanks, Vincent. I was wondering if you could have, like, do you include a prior knowledge of the repair actions in your estimation? So, well, the company knows when they have sent out something to repair it, so they
I know.
Can update.
And actually, this is like what you raise is general problem when you try to work on data issued from water networks, because these guys, like, they store many datas, but they're all around the places. So it was really hard to find ground truth on this repairing, on the appearances of leaks and so. So basically, if you would have liked to have a ground truth on the leaks appearing, it's not possible, because when they detect the leak, they know it's there for a long time, but they don't know when it appeared. And of course, they write down when they make some interventions, but it's not in the same database. And sometimes it's really hard to get it back. So we have, like, most of the problems we had in this project was communication with the people. And when we were asking something to get some feedback, because it was lost in gigantic databases and the crossing of these databases. So they have very little knowledge about how to really structure the data so that it appears neatly in data series. So I guess it's possible, but currently the way they deal with this, they use different tools which are not compatible together. So it's a work in itself to join all the data. Yeah.
If I rephrase the question, do you think that including that would have such a benefit that you could convince them to spend the effort in integrating their databases?
Well, the problem, then that's the second problem I don't understand, is that it took 2 people over 2 years of data to, well, a little more because there was the implementation also, but it took, let's say, 4 people full time during 3 years to make a tool which was comprehensible and everything. And even the biggest company in France did not do that for the past 20 years. So it means they have a real problem in putting money in that. Now, currently, they put lots of money into putting the sensor in place. And what they want is to get back a little for free, a little information about this massive amount of data. So they're not really keen into putting some money on efforts in doing so. Yeah, they're more keen on putting money in having artificial intelligence that can give them some feedback. But of course, it would help a lot. The more you see clearly that in this kind of problem, the more a priori you have, the better. Yeah. But this happened, like, we really were in a context where we just had the data and nothing else. So we had to figure it all by ourselves. But of course, I know it would help, but it's really hard to convince them. It's another world. Yeah.
Yeah. Thanks.
Vincent, I also have a question. Did you try to automate your procedures and to execute your algorithms on the whole database to be able to say, oh, you should look there?
Yeah, well, basically, this is a good question. So what we were able to do is we tested the mod. So I'm just going back to this first figure here. So we were able to test our model, so the predictive model, the water consumption model, on all of the sensors, and it was working quite well. So I didn't spend time on this, but on unseen sensor, it was doing well. When we tried to apply the tree topology, then you can see the first problem. All the black points here, all the black dots are all the sensors that are currently dead. All the red sensors are sensors that send the data, which is 0. And then the orange sensor and the green sensor are the one where we have data. So this is another problem, is that they put a huge amount of sensors. We could not test it on the whole structure. And another problem is that the way they place the sensor is really not well done. So you don't see it appearing here, but it doesn't look like a tree like I showed you, where like what I expected is kind of a tree structure with many depth level, yeah? But if you do the total sketch of this whole network, then it's one sensor at the top, then it's just like you have 50 sensors which arise just down there. And the whole strength of the strategy is to use this redundancy, yeah? Because the more floors you have in your tree, the more depth you have, the more redundancy you can use on the path of the water flow. But on this one, I think the highest depth that you can have is 3 or 4 on 80 sensors. It means they are all on level. So it also means, and this was also part of a project, to let them know also that the way they place the sensor is probably nice from a water consumption viewpoint. But if you want to go further and automatize this, then you have to think about other strategy of sensor placement, yeah? And this is something that will have to be done in the next years, because it's only starting now that they will be thinking in terms of both what we know from water management, but we also have algorithm can do lots of things, and they also have constraint on it. So how to place your sensor the best so that it fulfill your expectation in terms of water management and in terms of artificial intelligence, or whatever you want to call it, your tools, yeah? So the answer here is no, we could not fully test it on part of the work that was unseen. It's done quite reasonably well, yeah?
Thank you, Vincent. And I have another question. Did you try to compare your own method with the methods developed by people from diagnosis? I mean, usually they use the analytical redundancy, and they might use also parity space to formulate this. I mean, they also use graphs. Did you compare, or?
The problem here is that, so I know that all this kind of redundancy checks and everything. The real fact is that we struggled during the whole project, because if I present to you nice, like, what you should not forget is here I present you the story when you know the end. So I present you neatly that it appears as a simple matricial equation, then it goes to graph and things like that. But most part of the project was to formalize all this, yeah? You just had the problem, I have defaults, I have leaks, and just the fact that you come down to, okay, what is exactly the problem? How can I do that best? And things like that. If I know that, and I do that on purpose, I want to present such that it's the clearest possible. But of course, in the development of this project, it didn't go that, and we are quite happy that we could formalize it in the end. But most of the struggle was just to formalize the problem at hand that we had, yeah? So I didn't have time to do it, yeah? And now the project has come to an end, so we'll see how it further develops and how we can improve that, because now we know we have a neat environment, and of course we could check on the diagnosis part, yeah?
Thank you very much, Vincent, for your answer.
You're welcome.
Yes, thank you very much. It was a very nice presentation.
Thanks a lot. Thanks a lot, guys.
Are there any other questions? Okay, we are right on time. Maybe we can switch to Kevin's presentation.